Welcome to today's walkthrough of LeetCode problem number 951, Flip Equivalent Binary Trees. In this problem, we'll explore a fascinating concept involving binary tree transformations and equivalence checks. Let's dive into the problem details and approaches. In this problem, we are tasked with determining if two binary trees are flip equivalent. This means that, given the roots of two binary trees root 1 and root 2, we need to return true if they meet the criteria for being flip equivalent, or false otherwise. Now, two binary trees are defined as flip equivalent under specific conditions. First, if both trees are null, they are considered flip equivalent. Second, if the trees are not null, they must satisfy the following: their root values must be the same, and their subtrees must also align in a specific way. Either the left subtree of one tree matches with the left subtree of the other, and their right subtrees match as well, or the left subtree of one matches with the right subtree of the other, and vice versa. These conditions essentially allow for flipping the children of a node to align the trees structurally while maintaining their equivalence. Each tree is represented as a binary tree node structure. This means that a node in the tree contains three parts: a value, which is an integer, a left child, and a right child. These children can either be references to other nodes or null if there are no children. The output we are looking for is a Boolean value, true if the trees meet the flip equivalence criteria and false if they do not. To better understand this, let's look at some examples. In the first example, we are given two trees, root 1 and root 2. The input representation for root 1 and root 2 shows their structure. By applying a series of flips to the subtrees, we can transform root 1 to match the structure of root 2. Specifically, flipping the left and right subtrees of node 5 and root 1, and then flipping the left and right subtrees of node 2 and root 1, makes the two trees identical. Therefore, the output is true since the trees are flip equivalent. After the necessary flips, the trees in the first example become identical, which confirms their flip equivalence. Let's consider another example. In this case, both root 1 and root 2 are empty, meaning they are represented as null. Since the definition of flip equivalence explicitly states that two null trees are considered flip equivalent, the output for this example is true. Now, in the third example, the input shows that root 1 contains two nodes, with the root having a value of 0 and a right child with a value of 1, while root 2 is an empty tree. Here, we can immediately determine that the trees cannot be flip equivalent because one of them is empty and the other is not. For the third example, since root 1 is not empty while root 2 is empty, there is no possible way to align their structures, and the output is false. This demonstrates an important case to consider: when one tree is empty, the two trees are never flip equivalent. Moving forward, it's essential to recognize that the problem comes with a set of constraints. The number of nodes in the tree can range from 0 to 10,000, so we need to ensure our solution handles large inputs efficiently. Additionally, each node value is unique and falls within the range of 0 to 99. These constraints allow us to make certain assumptions about the input, such as not needing to handle duplicate values within a single tree. Finally, let's examine a few edge cases to solidify our understanding. If both trees are empty, the result is always true. However, if one tree is empty and the other is not, the result is always false. For trees with only one node each, they are flip equivalent as long as the nodes have the same value. In more complex cases, with large trees requiring many flips, it's crucial for the algorithm to handle these efficiently. Another scenario involves trees with completely different structures. If the structures don't align even after considering flips, they cannot be flip equivalent. Keeping these cases in mind will help ensure a robust solution to the problem. To start, let's consider a brute force approach using recursive tree traversal without any optimization. The primary intuition here is straightforward: for two binary trees to be flip equivalent, their corresponding nodes should satisfy the flip equivalence condition. Specifically, for each node pair, we verify two scenarios. First, we check if the nodes are equivalent without flipping their children. Second, we check if the nodes are equivalent when their children are flipped. The implementation involves recursively traversing the left and right subtrees of each node in both normal and flipped orientations. While the time complexity of this approach is proportional to the number of nodes in the smaller tree, specifically O, min, n1, n2, its space complexity is determined by the height of the smaller tree, O, h, because of the recursive call stack. However, this method has some drawbacks. It can be inefficient for very deep trees due to the risk of stack overflow, and it doesn't address redundant evaluations of the same subproblems, which can make it less optimal for larger inputs. To improve upon the brute force approach, we can use a memoized recursive traversal. The intuition behind this optimization is simple yet powerful. Since the equivalence of a pair of subtrees only depends on their structure and values, we can use memoization to store results of previously computed subproblems. This avoids redundant computations by caching results in a hash table, where each key represents a unique identifier for a subtree pair, and the value indicates whether they are flip equivalent. The time complexity remains O, min, n1 n2, but the space complexity increases slightly due to the storage required for the memoization table, while the depth of the recursive call stack remains O, h. On the other hand, we also have an iterative approach that uses a stack to compare nodes. Instead of relying on recursion, we explicitly track node pairs that need comparison. For each pair, we check equivalence in both normal and flipped forms, then push the child pairs onto the stack for further evaluation. This method is advantageous for avoiding stack overflow in deep trees, but its implementation can be more complex and less intuitive. Both of these optimized approaches provide alternatives to the brute force method, each with its own trade-offs. Among the approaches considered, we chose the recursive tree traversal without optimization as the preferred strategy. This choice is based on its simplicity and clarity, which make it easy to implement while still being effective for most practical cases. The intuition aligns well with the natural structure of binary trees. For two trees to be flip equivalent, their subtrees must also satisfy the same condition recursively. Key observations reinforce this choice. First, flip equivalence is inherently recursive, and the problem's base cases, such as null nodes being trivially equivalent, guide the recursion effectively. Second, the depth-first nature of the recursive solution fits seamlessly with the binary tree structure, allowing us to evaluate equivalence in a straightforward manner. Given the constraints of this problem, the recursive approach strikes a good balance between simplicity and performance. While other methods like memoization or iteration can offer advantages in certain scenarios, their added complexity doesn't provide significant benefits for the typical input sizes encountered here. When comparing the chosen approach to the optimized methods, there are some clear trade-offs. Unlike the memoized recursion strategy, the simple recursive traversal avoids the overhead of maintaining a hash table, which makes it faster for small to medium-sized trees. Compared to the iterative method, recursion is more intuitive and aligns better with the inherent recursive nature of the problem. However, the main limitation of this approach is the risk of stack overflow in cases of extremely deep trees. That said, this risk can often be mitigated in practical scenarios where constraints are placed on input size. In terms of complexity, the recursive traversal has a time complexity of O, min, n1, n2, where n1 and n2 represent the sizes of the two trees. The space complexity is O, h, where h is the height of the smaller tree, due to the recursion stack. In conclusion, this method is preferred for its simplicity, natural alignment with the problem structure, and competitive performance under typical constraints, making it the best fit for this problem. To determine if two binary trees are flip equivalent, we need to consider both their structure and values. Two trees are considered flip equivalent if they are either structurally identical or can be made identical by flipping the left and right children of some nodes. To solve this, we begin with the base case. If both nodes being compared are null, the trees are trivially flip equivalent, so we return true. However, if one node is null and the other is not, the trees cannot be equivalent, so we return false. Next, we compare the values of the current nodes. If the values differ, we return false since flip equivalence requires matching values. Finally, we handle the recursive structure check. Here, we explore two possibilities for each pair of nodes. The first is the case where no flip is needed, meaning we compare the left child of the first node with the left child of the second and the right child with the right child. The second possibility involves flipping, where we compare the left child of one node with the right child of the other, and the right child with the left. By exploring both cases, we account for all possible configurations that could result in equivalence. If either the unflipped or flipped comparison returns true for a pair of nodes, we can conclude that the current nodes are flip equivalent. Otherwise, we return false. This logic extends recursively to all descendant nodes. To combine the results, we apply the same process at every level of the tree, ensuring that equivalence is maintained across all subtrees. Now, there are some key insights to highlight about this approach. First, flip equivalence is naturally a recursive problem because the equivalence of the entire tree depends on the equivalence of its subtrees. Second, symmetry plays a crucial role. By considering both flipped and unflipped configurations at each node, we ensure that all possible ways the trees could align are checked. Lastly, handling base cases like null nodes and mismatched values early is critical. This prevents unnecessary recursive calls, improving the efficiency of the algorithm. In terms of data structures, the algorithm operates directly on the nodes of the binary trees, and the recursion uses the call stack to keep track of comparisons as we traverse the trees. Now let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the number of nodes in the smaller of the two trees. Each node is visited exactly once during the traversal, and at each node, we perform a constant number of comparisons. The space complexity is O(h), where h is the height of the tree. This comes from the recursive call stack, as the depth of the recursion corresponds to the height of the tree. To better understand how this works in practice, let's walk through an example. Consider two binary trees. Tree 1 has the root node 1, with left and right children 2 and 3. Tree 2 has the same root node 1, but the left and right children are 3 and 2 respectively. Continuing further, Tree 1 has children 4 and 5 under node 2, while Tree 2 has children 5 and 4 under node 2. We start by comparing the roots of both trees, which have the same value of 1. Since the values match, we proceed to compare their subtrees. We now examine the left and right subtrees of the root nodes. First, let's check the unflipped case. We compare the left child of Tree 1's root, which is 2, with the left child of Tree 2's root, which is also 2. Similarly, we compare the right child of Tree 1's root, which is 3, with the right child of Tree 2's root, which is also 3. Since both pairs match, we move further down the trees. For the left child 2, we compare its children, 4 with 4 and 5 with 5. These match as well. For the right child 3, both are null, so they also match. Now consider the flipped case. If we compare the left child of Tree 1's root with the right child of Tree 2's root, we get 2 and 3, which do not match. Similarly, comparing the right child of Tree 1 with the left child of Tree 2 results in another mismatch. As a result, we discard the flipped configuration. Since the unflipped case works, we conclude that the trees are flip equivalent without requiring any flips. This example illustrates how the algorithm systematically checks both configurations to determine equivalence. This solution implements a recursive function flipequiv to determine if two binary trees are flip equivalent. The problem is solved by comparing the structure and values of the two trees. ####line by line explanation. 1. Base case, line 3, if both current nodes are null, they are trivially equivalent, so we return true. 2. A mismatch condition, line 6, if one node is null and the other is not, or if their values are different, we return false because the trees cannot be made equivalent. 3. Recursive check, line 10, we handle the two possible scenarios. No flip case, compare the left subtree of root 1 with the left subtree of root 2, and the right subtree of root 1 with the right subtree of root 2. Flip case, compare the left subtree of root 1 with the right subtree of root 2, and the right subtree of root 1 with the left subtree of root 2. If either scenario evaluates to true, the trees are flip equivalent. The recursion continues until all nodes in both trees are processed or a mismatch is found, ensuring correctness. This approach ensures that the function checks all possible ways the trees could be structured to be equivalent. ###complexity. Time complexity, O, min, n1, n2, where n1 and n2 are the number of nodes in the two trees. Each node is visited once. Space complexity, O, h, where h is the height of the tree, due to the recursive call stack. This solution is efficient and directly addresses the problem requirements. Here, we begin defining the Java solution for checking if two binary trees are flip equivalent. The method flipequiv takes two parameters, root 1 and root 2, which are the roots of the two trees we want to compare. First, we handle the simplest case. If both nodes are null, meaning we've reached the end of both trees simultaneously, they are considered equivalent, so we return true. Next, we account for cases where one node is null, or the values of the two nodes don't match. In either situation, the trees cannot be equivalent, so we return false. Finally, we evaluate the core condition for flip equivalence. There are two possibilities to consider: either the left and right subtrees align without flipping, or they align by flipping the left and right subtrees. To check both scenarios, we recursively call flipequiv for the corresponding child nodes and combine the results using a logical OR operator. Additionally, we define the tree node class used to represent the structure of each node in the binary tree. A node contains an integer value, val, and references to its left and right children, which are also tree node objects. The class includes two constructors. The first initializes a node with a value but no children, while the second allows us to directly specify both the value and its left and right child nodes. This design makes it easy to construct and manipulate binary trees while ensuring the nodes maintain the relationships required for the flip equivalence checks. Here, we start with an example where no flip is needed to determine if the two trees are equivalent. The input trees both have a root node with the value 1, and each root has two child nodes, 2 and 3. First, we compare the root nodes of both trees. The values match, so we proceed to compare their subtrees. Starting with the left children, we find that both nodes have a value of 2, and since these nodes have no further children, the recursive calls confirm that the left subtrees are equivalent. Similarly, we compare the right children, both of which have a value of 3, and again, with no further children, the recursive calls confirm that the right subtrees are equivalent. Since both the left and right subtrees match without any flipping, the trees are flip equivalent. In the next example, we explore a case where a flip is required. The input trees each have a root node with the value 1, but the left and right children of these roots are swapped. First, we compare the root nodes, and since their values are equal, we proceed to their subtrees. Comparing the left children, we see that the value of tree 1's left child is 2, while tree 2's left child has a value of 3. These values do not match, so we check if flipping the subtrees can resolve the mismatch. We then compare tree 1's left child with tree 2's right child. When comparing tree 1's left child, which has a value of 2, with tree 2's right child, also with a value of 2, we find that the values match. Since neither of these nodes has further children, the recursive calls confirm that this part of the subtree is equivalent. Next, we compare the right children of tree 1 and tree 2. Tree 1's right child has a value of 3, while tree 2's right child has a value of 2, so these values do not match. Again, we check for flip equivalence by comparing tree 1's right child with tree 2's left child. Here, both nodes have a value of 3, and with no further children, the recursive calls confirm equivalence. Since the subtrees were found to match after flipping, we determine that the trees are flip equivalent. Finally, we examine an example where the trees are not equivalent. The root nodes of both trees have the same value, 1, so we move on to compare their subtrees. The left child of tree 1 has a value of 2, while the left child of tree 2 has a value of 4. These values do not match, so we check for flip equivalence by comparing tree 1's left child with tree 2's right child. However, tree 2's right child has a value of 5, which also does not match tree 1's left child. Since no matching structure is found, we conclude that the trees are not flip equivalent and return false. The time complexity of the flipequiv function is determined by the number of nodes in the smaller of the two trees. As the function processes the two trees, it starts by comparing the values of the current nodes, which takes constant time, or O1. It then proceeds to make up to 4 recursive calls, 2 for comparing child nodes without a flip and 2 for comparing them with a flip. However, thanks to the short-circuiting behavior of the OR operator, only 2 of these recursive calls are actually executed. This means that each node in the smaller tree is visited once, and the recursion processes at most 2 child nodes for each visit. As a result, the total number of recursive calls is proportional to the number of nodes in the smaller tree. Therefore, the overall time complexity of the function is O, min, n1, n2, where n1 and n2 are the number of nodes in the two trees, root 1 and root 2, respectively. The space complexity of the algorithm is primarily determined by the depth of the recursive call stack. At any point during execution, the maximum depth of the call stack corresponds to the height of the smaller tree, denoted as h. In the worst-case scenario, where the tree is skewed like a linked list, the height of the tree is equal to its number of nodes, which means the space complexity becomes O, min, n1, n2. On the other hand, in the best-case scenario where the tree is perfectly balanced, the height of the tree is approximately logarithmic with respect to the number of nodes, resulting in a space complexity of O, log, min, n1, n2. This demonstrates how the space usage of the algorithm adapts to the structure of the smaller tree. If we compare this optimized approach to a brute force method, the difference in efficiency becomes clear. A naive approach would involve generating all possible flipped versions of one tree and comparing each version to the other tree. This is computationally prohibitive because the number of possible flipped versions grows exponentially with the size of the tree. Specifically, for a tree with n nodes, there are 2n1 possible flipped versions. Comparing all of these versions would result in a time complexity of O(2n1*n), which is entirely infeasible for larger trees. In contrast, the optimized solution avoids generating these flipped versions altogether. Instead, it uses recursion to directly compare the two trees, making the process much more efficient. This reduces the time complexity to O, min, n1, n2, which is a significant improvement over the brute force approach. The best, average, and worst-case scenarios for this algorithm help us understand its efficiency under different conditions. In the best case, the two trees are nearly identical, and the initial recursive calls quickly confirm their equivalence without needing to explore further. While the time complexity remains O, min, n1, n2, fewer recursive calls are needed in such cases. In the average case, the trees may have some structural differences, but the recursion efficiently prunes subtrees that don't match, maintaining the time complexity at O, min, n1, n2. In the worst case, the trees are completely skewed with maximum depth, requiring all nodes to be compared. Here, the recursion depth reaches its maximum, leading to a space complexity of O, min, n1, n2. Regardless of the case, the algorithm visits each node once, and since each recursive call processes two children, the overall time complexity remains linear with respect to the number of nodes. The space complexity, however, is directly influenced by the height of the smaller tree, confirming its dependency on the tree's structure. When working with flip-equivalent binary trees, there are a few common mistakes to watch out for. First, one of the biggest errors is failing to account for both possible configurations at each node. Flip equivalence means that subtrees can either be in their original order, left and right, or flipped, where left connects to right and vice versa. Ignoring the flipped case will lead to an incorrect implementation since both configurations need to be checked recursively. Another common mistake is not handling null nodes properly. This happens when you assume both trees are non-empty or forget to check cases where one subtree is null while the other is not. Remember, a null node cannot be equivalent to a non-null node, so you must include explicit null checks in your logic. Lastly, inefficient recursive implementations without memoization can cause performance issues. Recursion without caching results may lead to repeated computations for the same sub-problems, especially in larger or more symmetric trees, resulting in exponential time complexity. Addressing these pitfalls is key to building a robust solution. Additionally, incorrect base cases in recursion are another frequent issue. For example, if you don't account for all scenarios, like when both nodes are null, which indicates equivalence, or when one node is null and the other is not, which makes them non-equivalent, you might run into infinite recursion or incorrect outputs. Getting the base cases right is absolutely essential for recursive algorithms. Another mistake is overcomplicating the solution by introducing unnecessary data structures, such as arrays or lists, to store node values. This approach not only increases space complexity but also makes the code harder to read, debug, and maintain. Directly comparing the nodes as you traverse the trees is a simpler and cleaner strategy. Keeping your solution streamlined and focused on the problem requirements is often the best approach. In interviews, there are a few critical points to keep in mind when tackling this problem. First, focus on mastering the fundamentals of recursion, especially handling base cases correctly. Interviewers often prioritize clarity and understanding over optimization, so starting with a correct brute force solution and then discussing improvements like memoization is a strong strategy. Be prepared to analyze the time and space complexity of your solution. For instance, a naive recursive approach might have exponential time complexity, but with memoization, you can reduce this to O(n). It's also important to ask clarifying questions early on. For example, confirm whether the trees are strictly binary, if node values are unique, and whether the input guarantees valid trees. Finally, this problem is closely related to others like same tree, subtree of another tree, and invert binary tree. Understanding these problems can provide additional insights and techniques that may help in solving flip equivalence efficiently. There are alternative approaches you can consider for solving this problem, each with its own trade-offs. One option is a recursive approach with memoization. This reduces time complexity by storing results of previously computed subproblems, which is particularly helpful for symmetric trees. However, it comes at the cost of increased space complexity because of the memoization table. Another approach is iterative, using a stack to traverse the trees. This avoids recursion, which can be advantageous for very deep trees where stack overflow might be a concern. However, iterative implementations tend to be more complex and less intuitive compared to recursion. Lastly, you could use tree canonicalization, where both trees are transformed into a standard form, such as sorting their children, and then compared. While this simplifies the comparison process, it requires additional preprocessing, which could be computationally expensive for large trees. Each method has its strengths and weaknesses, so the best choice depends on the specific requirements and constraints of the problem. To wrap up, we tackled the concept of flip equivalence in binary trees and walked through a recursive solution. We highlighted its time and space complexities, along with key takeaways for tree problems. Thanks for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!